Hello. This is going to be talking about Chapter 13 today in conjugated systems. Conjugated systems work a little bit differently than the sort of regular alkenes that would. They have some kind of quirky properties to them because you can deal with resonance structures, some of that, and so that makes them a little more complicated. With that, and so, for example, so if you have a radical here, right, next to a double bond, you can do a resonance structure where you can actually move that radical around, right? So one electron. So remember, in this system, there's two electrons here in that pi bond. If we can take one of these and move it there, one of them moving there, and then we had to figure out something to do with this electron, and so we can move it there. And so the resonance structure looks like this. So now here are those two electrons, and then the radical is right there. So this is having this next to the allylic radical or allo radical can provide some stability to the molecule. So it's not just this carbon that has to do with the radical. You can help share the load with this one. So it's sort of, if you think of the resonance hybrid, it's sort of like this, where it's sort of a half bond, half double bond for each one on each carbon. Same thing happens with a positive charge, right? Or charge systems, right? We can move this over, right? Because this one you have two electrons or two hydrogens on it. So once you make the fourth bond, so push it over here. So the carbon or the positive charges can be both carbon 1 and carbon 3 can hold that burden, something like that. So it's sort of the best way that I can describe it is to think about moving a couch. If it's just one person moving a couch, it's going to be quite difficult. If you have two people carrying it, it's reasonable. If you have 3 or 4 people helping you move the couch, is even easier, right? So same thing here. If you have only one carbon bearing that full charge, it's going to be quite difficult. But if you can have 2 carbons taking the load, it'll be just fine. And so the reason why we can deal with this is the fact that all of these carbons here in this system, and even the ones down here, they all have p orbitals that are free, that are unhybridized, and so they're all pointed in the same direction. And so what happens is they all kind of smear together. Here. These 2 carbons don't have, they're just sp3s, so they don't have a free p orbital. But when you have a whole bunch of them right next to each other, they smear together and they can move those electrons in and out, onto the different carbons. Okay? And so what ends up happening is, if you have a carbocation, right? We think about tertiary being the most stable, right? So, but if you have a tertiary next to an allylic center where you can do the resonance hybridization to stabilize it, that's really good. You look at this and say, "Oh my goodness, this is a primary carbocation. That's bad." But because we can do the resonance structure to move this over, because there's a double bond here, this is actually quite stable, and as it goes on. Now you'll notice that here, if it's actually the positive charge carbocation actually on the double bond, that's actually quite bad because the orbitals they're going to be 90 degrees from each other. So if the p orbitals for the double bond are like this, the charge is going to be like this, and so they're not going to be able to help out each other. Something like that. So this is actually really, really unstable. Okay, so just as a reminder for writing resonance structures. Okay, so for one thing, right? So if you think about the arrows, each arrow signifies something else. So if you have just a straight arrow, straight double bond arrow, that's a reaction. Okay. If you have 2 arrows going back to this, or sometimes I'll write it like this, doesn't really matter. This is an equilibrium. Reaction's an equilibrium. Okay. The other thing would be a double-headed arrow. Okay, so single-headed arrows mean reaction. Double-headed arrows, right? Remember, indicate resonance. Okay. And if you have a curved arrow, okay, either double barbed, right? That's indicating 2 electrons. This one, 1 electron. So this is electron flow. So how are the electrons are going from what atom to what atom? Okay. So first thing we're writing resonance structures is, remember that atoms cannot move. The only thing that can move are electrons. And you can't violate the octet rule. So unless unless it normally can. Okay, but carbon can't have more than 4 bonds, right? It can have 3, it can have 2, that's fine. But it can't have 5 bonds. Same thing with oxygen, carbon, or nitrogen, oxygen, fluorine, things like that. Now some of them, sulfur, things like that, phosphorus, they can violate it, but there's specific reasons for that. But it has to be a valid structure. The resonance structures have to have the same number of unpaired electrons. They also have to have the same net overall charge on the molecule. The delocalized, they have to lie in a plane or be nearly planar, right? So it was like this part here, right? So you have a charge, and you have the p orbitals, but since they're right on top of each other, they're at 90 degrees. So they have to be it has to all be in alignment. And usually, the atoms, participate. They need to satisfy at least one of these. Now, there's some exceptions with the charge, some notable exceptions to the ammonium type ion, so that can't. But in general, if it has a charge, it's good. It's part of a pi bond, carbon-carbon pi bond, carbon-oxygen pi bond, whatever, or it has a set of lone pair electrons. So that if it satisfies this, any of these, then it can participate. If it doesn't, well, it can't participate in there. Now, as a general hint, there's usually a charge involved with a lot of these resonance structures. So if there's a charge, think about starting there. Okay, it has a charge because it doesn't have what it normally wants. Carbon wants no bond or 4 bonds. Right? So that oxygen wants 2 bonds, two lone pairs. Right? So that nitrogen usually wants to have 3 bonds, 1 set of lone pairs. If it doesn't have that, it's going to have a charge, and it's going to try to, and you have to figure out why, try to get it to a better situation. Okay, so for writing resonance structures, right? So these are fine, right? This one is not, right? That carbon there, right? It doesn't have a charge. It doesn't have lone pairs. It doesn't have pi bond. Lone pairs, what is it? Charge, lone pairs, double bond. Okay, so this can't participate. So these two are fine. This one is not. What you would end up having to do is move a hydrogen over. That's not going to happen. Okay, you can shift this over. I suppose in theory you could, but the problem is now this carbon has 5 bonds. You're violating the octet rule. This isn't going to happen. Okay. You're not going to have a situation where you're trying to minimize the number of, say, radicals in the molecule, right? You don't want to go from 1 to 3. Yeah, in theory this could happen, but it really does not happen. So it'd rather, if this is going to move over, it's going to come in and make a bond, right? So resonance hybrids, right? It's going to be a combination of these two, right? But in reality, this is what it really is in the real world. But it's easier to think about these. Okay, these are sort of a construct of being able to do this because this is easier for us to imagine. Okay, so when you estimate the stability, the more of these that you can satisfy, the more stable it is. So we want to have more covalent bonds. The more covalent bonds, the better. The more atoms with a full octet, even better. Okay, and you want opposite charges to be near each other. Right? So if you have a north and south magnet, right, you try to pull them apart, right? It takes energy to do that. Right? It takes oomph, depending on the magnets, right? So what you don't want is, so here, right, everybody has their bonds filled, more covalent bonds, right? So, just look at the pi bonds, right? This has 2, this one only has 1, this one as well as 1. Also, the charges are fairly far away. That's not good. So, it's twice. Also, this, when you go from here to here, this one, everybody has their octet filled. Now, the oxygen has a charge, and that could be an issue. But that's okay. So this is probably going to be more stable because it's everybody has their octet. Here, right, so this is going to be less. This is going to be less stable because right, this one has, you have charge separation here. Okay, these guys are not right next to each other. That's not good. Okay, so draw the possible resonance structures. Which structure is the most stable? Okay, so this is just a reminder. Now, with this one, what you're going to want to do is you're going to want to draw in the hydrogens. It's the easiest thing to do. And so if you have this structure here, draw lone pairs. So we know there's a positive charge here, so that means it only has 3 bonds. So it has 1 carbon-carbon bond shown, so that means that there's 2 hydrogens. So 3 bonds shown, so 1 hydrogen. This carbon here, 4 bonds shown. Here, 2 bonds shown, so CH2. Here it's the CH3. Now, this can participate because there's a charge. These two can participate. These 2 carbons can participate because they're part of a double bond. The oxygen can participate because it has lone pairs, but these can't. Right? These 2 carbons, right? They just have single bonds, no charge, no lone pairs. So we can sort of, with thinking about the resonance structure, we can kind of ignore them. Okay. So what's going on here? Right? So that this carbon, right, it only has it has 3 bonds. It wants a 4th one. Right. So it needs to look at its neighbor. And so here, what we can do is we can the neighbor. That neighbor's going to help out. And so we're going to get this. So now this carbon only has 3 bonds. Okay, now you can't help with this one. These guys can't help out. We could slide this back over, but that would just be this. Okay, the other option is to use the oxygen here. And this one, what we do is we take these lone pair and move them down. And so there we go. So what do we have? What are we looking for? Right. So this one, trying to figure out this stability. Right. We want more covalent bonds. We're just looking at the pi bonds here. So 1, 1, and then this one has 2. So that's good. Everybody has their octet filled. Okay. So even the oxygen, right? So 2, 4, 6, 8. Okay. Here, this one didn't have its octet filled. Neither did this one. And there's only 1 charge, so we don't have to worry about charge separation. So this is going to be the most stable. Okay. There you go. Now, with polyunsaturated, okay, so all that means is that we have a link between double, single, double, single, double, single. It doesn't matter if it's in a chain or if it's in a ring. Okay, and so these all have double, single all around, or within the molecule. These do not, right? So here they're right double double. Okay? Here it's double, triple, double, double, or excuse me, triple, single, single, double. That's not good. Here there's these 2 single bonds in between the doubles. So but these are all conjugated. Okay? Now you can do the allene. Okay, so the accumulated double bonds, and so this has a certain structure, and sort of how the orbitals are sort of put together is like this. And so these 2 are in the plane, and these 2 hydrogens are out like this. And so it's kind of a cool little structure. So you'll see this called as an allene. Okay, if there's separation, right? So so as long as this isn't more than, actually it's just isolated more than 1, right? 1 is the same. Okay, I see what they're doing. So you can have double, single, double, and that's fine. But if you have anything more than that, so like that, so double, double, single, single, double, it's not conjugated. Okay, so these will appear shorter, right? So they're also single bonds, right? So you can get rotation around them. Okay? So like that, and so you can have 2 forms. You can have this S-cis conformation. You can have the S-trans conformation. The double bonds point double bonds pointing like this, or the double bonds pointing like this. So this is the cis because they're both pointed in the same direction. Trans because they're pointed opposite way. Okay, you can get rotation. Okay. Now, getting in the acis, you're going to have to pay a penalty, right? Because when they're in this conformation, these two hydrogens are going to knock heads. Okay, they're going to be hitting each other. Okay, so it's probably going to want to spend a lot more time in this configuration. Okay. Now, don't forget that these four, because it's all four of these carbons have p orbitals, they're all going to align and sort of smear into each other, overlap. Now, having this conjugated system, all it's saying is that it's actually more stable than it should be. So if you just take two single alkanes, or alkenes, whatever, you get this kind of energy. Remember, the more energy it gets out, right, the less stable it is. And so this right here, it's actually 15 kilojoule per mole more stable than you would expect. So from this way, or from either one of these, again, you're going to get this extra 15 kilojoule per mole of stability. That's what this is saying, is that when you have the conjugated system, it's more stable than the double bonds separately. Okay? Now, we can use this, okay, these conjugated systems, and we can actually detect them in UV spectroscopy. So visible light, so ultraviolet visible, using those lights. So you're talking about anywhere between roughly 200 to 700. So now, just as a reminder, with the with wave, when we're talking about light, right, we can talk about wavelength, which is peak to peak, okay, or trough to trough, but at that distance, okay, it's usually in nanometers or something like that. Now, the frequency is as it's moving along, how often do you get a peak? Okay, how many peaks per second? Okay, cross bond. And if you want to look at energy, it's some of that, and so you end up getting this equation where energy is equal to Planck's constant, which is just a number, the speed of light divided by the wavelength. Okay, and so as this goes up, as this increases, this goes down. And so same thing. As this wavelength shrinks, so as the wavelength gets shorter and shorter, right, peak to peak distance, this energy is going to go up. So there's an inverse relationship between the two. Okay, and so what we can do is we can. It turns out that different functional groups or different types of conjugations that are going to absorb a different light or at different wavelengths, and then absorb different amounts of light. And so what you can do is you can put your light source in here and then split it. Okay, one going through a reference and one through a sample. And so you know how much. So if you know how much light is going here, you can compare it to what's going on here and see at the different absorbance levels. And so at different wavelengths, this system, usually we talk about the peak, the wavelength at which there's maximum absorbance. So here it'd be like 241 or something like that. Okay? And this is so that's where we're going to take a look at it. Right? It does some absorbance here, at the other wavelengths, but this is the maximum wavelength. Okay, so this molecule is going to absorb that light relative to the reference. Okay? And we can use that doing Beer's laws. So how much absorbance? So with that, so absorbance is equal to this molar absorptivity. So you'll hear me call it extinction coefficient. It's just how much does it typically absorb per mole, something like that, or per centimeter. The path length of light, this is almost always 1 centimeter, although it doesn't have to be. This one here, so if you had a 2 centimeter sample, as you shine the light through, right, it's going to interact with twice as much material, and so it's going to absorb twice as much light. So as it's going through, so we have to take that into account. And then the last one would be the concentration. It's typically in molar. So this right here, the molar absorptivity, that's a property of the molecule. You have to go to the big book of molar absorptivities and look it up. Usually you just do a Google search, but every molecule is going to have a different number, and you just have to look it up. Okay, and typically what happens is, it's twice. Typically what happens is I'm going to give you three. You have these 4 variables. I'm going to give you 3 of them. You got to figure out the last one. Okay, So with that, so here you go. So calculation, right? So absorbance is 0.78. Concentration of the sample is that. The length of the sample travels 1 centimeter. What are the units? Okay, this is calculate the molar absorptivity. And so what you're going to do, right? So this is absorbance. This is what we're looking for. 1 centimeter path length, 1 centimeter cuvette, and then this is the molarity. You come in here, and this is your molar absorptivity. Notice that the wavelength of light is not in this calculation. Okay, you could say that it absorbs at, I don't know, 500 nanometers. That doesn't make a difference. Okay, it's not part of the equation. It does not matter. Now, one of the things that we have noticed is that as you get longer and longer conjugation, you increase the general rule is that you increase the wavelength of light that it absorbs. Okay, so going from basically no conjugation is 161, but if you go to 2, right, you end up double, single, double, right? Double, single, double. It's longer, right? And if you get a whole long double, single, going all the way across, right? It's even more longer wavelength of light. Okay, and so, but if we were to say break it, react it right there, okay, then it would be a much shorter wavelength because you'd have here and here. So. Now, one of the things that can happen is what are called 1,4 additions. This is where things get messy in a hurry, right? So if we had just a regular HCl, or if we just HCl added it just to a regular alkene, right, you would end up getting this, right? So assume that that's not there. Okay, that's what you would get. But it turns out that when you do this reaction, you actually get a little bit of this, the 1,4. So 1, 2, 3, 4, right? So but that's you're going to get not only 1 and 2, but you're going to get 1 and 4. 1, 2, 3, 4. Okay. So why does this happen? And this is the answer to all of the questions are all exactly the same. Okay. So what the heck happens? Okay. So you get so this one here it's because it's symmetrical, it's a little bit easier. But what ends up happening, right? HCl. Right. So remember, this is a polar covalent bond. Okay, so you're going to pick one of the double bonds, and you would react here, push that away, so you'd end up with this intermediate, right? The H is going to go in this side, so you can have the positive charge here, right? So you think about it, this is secondary, but this is primary. Okay. The other issue with this is the fact that you want to be right next. You want to be right next to the double bond here to take advantage of the resonance, right? So that because we can get a resonance structure like this, okay? Like this, and get a positive charge there, right? Oh, we also end up making a Cl minus. Okay? And so we can react here or here, right? So if it sees this molecule, right, the molecule would look like this. If it sees this molecule when it reacts, it'll be here. Now, what you would do is you would actually do this again, do this whole thing, but then starting with this double bond. But in fact, you actually end up making the same products because it's symmetrical. Okay? But you're not going to want to put the double bond. You're not going to get. This isn't going to happen. You're not going to get the H adding here, but the carboxylic adding here for 2 reasons. One, it's primary, but the bigger reason is it's not next to the double bond. Okay, that makes it much, much, much more stable. So it's just not going to want to go here. Okay? So that's not going to happen. You can also get 1,4. This is actually 1,6 addition. So like that, and so you can add it here. You can add it here, and then actually do the resonance structure where it gets over to here. So it's actually 1/6 addition. It's kind of cool. Okay, so how do we do this? Okay, so this works the same way each time. So we have. So this is adding one. Let's do HCl because that's a little bit easier to see. Okay. So adding HCl. So, choose a double bond. So this is on the left, so we'll try this one first. So this is going to react here, over there. Okay, so we're going to end up Right? We're going to want to put that hydrogen in there so that the positive charge goes next to the double bond. We didn't do anything with that double bond. It's still there. Right? Plus Cl minus. Okay. Now, we can do a resonance structure where that comes over there. And then the positive charge is there. Now, if the chloride sees this resonance structure, it'll attack there to make this. If it sees this resonance structure, it will attack there. There we go. Now, the other option it could do is it could use this double bond, attack there, push that away. If we did that, it's going to want to put the hydrogen here, the positive charge there, so it's right next to the double bond. Okay, plus Cl minus. Again, we can do a resonance structure. That goes there. Now, it's not going to be very happy when it does this. That's not what I asked you about. I asked for the possible ones. So hydrogen was there, so we're going to put it there. So, if the chlorine sees this resonance structure, it's going to attack there to make this. If it sees this resonance structure, it's going to attack there. There you go. Here are your four. There you go. Here are your four products. Okay. Now, probably the most likely outcome is probably going to be this one because you end up making a tertiary carbocation. So it's most likely this is probably going to be the highest yielding. But I didn't ask you about that. I just asked you about draw me the four structures that are going to be produced. And you do it the same way. You get one of the double bonds, comes in and attacks, displace, do the resonance structures, and then the chloride is going to attack each of the two resonance structures. Now, start over, and instead use the other double bond to attack, and do the same thing. Right? So you're going to put the positive charge next to the double bond, you'll get the resonance structures, and then the nucleophile will come in and attack where that positive charge is. That's how they all work. Now, for thermodynamics, okay, now this is, usually there's a collective shudder when I talk about thermodynamics. But what's happening here is what's called kinetic control and thermodynamic control. It's various thinking about this on a very high level. Okay, so what can happen is if we do this HBr, the 1,2 adduct at low temperatures, at low temperatures, it actually favors the 1,2 adduct. At higher temperatures, it's the 1,4. Okay? And so this change of temperature, can determine how this reaction, proceeds. So why is that? Okay. Well, it turns out that the blue one, which is the 1,2 at lower addition, it has a lower activation energy. Okay. And so but the overall energy is less that it gets out at the end, but it's still okay. The 1,4 product, which is the magenta here, this is it takes a lot more energy to get to it and to get over the activation barrier. But in the end, it's a better product thermodynamically. Okay, and so what's happening is, when it's cold, running this at 0 degrees C, right, we don't have enough energy to go over this activation barrier. Okay, but it's still at a pretty high energy, and so what's going to happen is it's going to take what it can get. Okay, and so it's going to at least go over the little hump and get here. Okay, for this one here, right, for the 1,4 adduct, right, what we need to do is give it more energy. How do we do that? We heat it up. And so what it really wants to do is to go over this larger hump so it can get the lower energy. Okay, so the visual I do is thinking about, if you're a kid, you have two grandmothers. One lives a block away, and one lives a mile away. Okay, so the one that lives closer generally has, she's got cookies. Okay, so with that, but you know, the other grandmother that lives a mile away has, I don't know, some, you know, chocolate pie a la mode. How about that? So, I don't know, something crazy like that. So, if Mom says, we got to go, we have to leave in 15 minutes. Stuff like that. So, well, in 15 minutes, you can run down to grandmother's house and go get a cookie. To the one that's close, you can go a block down, grab a cookie, you know, give grandma a kiss and run back. And hey, you got yourself a cookie. If you only have that amount of time, you get what you can get. Okay, but if you say like we have to leave in 2 hours, well, that's certainly enough time to go the longer distance, right? Spend the more energy. Because then you can get to the grandma's house a mile away to get pie a la mode, stuff like that. And so this is really, really want to get, right? As opposed, but at low temperatures you get what you can. Okay. So if under cold conditions, you favor the kinetic product because it's what you can get at low temperatures, because it's what's going to be fast, easier to get in the short run. Thermodynamic, if you heat it up. Under high temperature conditions, that's the thermodynamically better product because under cold conditions you're going to go over the smaller activation energy. Under higher temperature conditions, you're going to want to get to the lower end here. So that's all this is. So the Diels-Alder reaction. So this is a nice reaction. It's technically a 4+2 cycloaddition. This is a nice way of making cyclohexanes. Like that. So it works really well. So that is Diels-Alder were two professors who discovered this. So and what's going to happen is you have a diene. Okay, so it's 2 enes, right? So it's they're in conjugation, double, single, double. Okay, so we're going to have this general structure about them. Okay, so it's 2 alkenes, conjugation, and then you have what's called the dienophile, the thing that likes the diene. Now, typically this is an alkene. It doesn't have to be an alkyne as well. We'll talk about this. So what ends up happening is you get this mechanism. Okay. The diene, and then you have the dienophile. What happens is you get this. This bond goes here, so you make a new carbon-carbon bond here. This bond ends up going down there to make a new carbon-carbon bond, and then this one slides this way. So your product ends up looking like this. Got the double bond back here. But you're going to make a new bond here and a new bond here. And so that's your general structure. Okay? So that. So for what you're going to make. So now we've made 2 carbon-carbon bonds, which is always good. Okay. So the diene, okay, and then the dienophile. You're going to go through this intermediate here that looks amazingly like very similar to a benzene ring to make a cyclohexane. Now, one of the things that has to happen with the diene is that it has to be in this S-cis configuration. Okay, so that these two carbons are near the dienophiles to make the bond. Okay, if if this carbon's pointing away, this is too far away to make a bond. Okay, with that, so it has to be in this S-cis configuration. Okay, so what that means is that if it's locked like this, if the diene locked like this is never going to happen. Right? There's no way that you can get rotation here. Here, it's going to be really, really, really slow because while it can rotate, right, rotate around this double bond here, when it does that, these 2 methyl groups here are going to be coming together and really knocking heads. And so it's going to take a huge amount of energy to get it into this configuration to do the Diels-Alder. So it's just not going to happen. It's going to happen. If it happens really, really slowly. Okay? But if it's locked in the S-cis configuration like this, it goes very rapidly. Okay. Now in this case here, we're going to make this structure here. Here's the 6-membered ring. Okay. Here it is right there. Okay. If you look at it from the side, it's like this. This CH2 here is just this CH2. It's bridging between this carbon and that carbon. here, and here. We haven't done anything with it. It's still there. It just kind of has to get out of the way. Okay? And stuff like that. And so here, right, this is in this configuration. And so you can, here's the 6-membered ring that you just made. But notice how we had a triple bond to a double bond, right? Normally it goes, well, you use one of the pi bonds to make a new bond here, right? So it usually goes double to single, but you can go triple to double. That's totally fine. Okay, and again, we've got these two CH2s here that are bridging between, that are connected to this carbon and this carbon, and they're still there, and so they're kind of coming up like this. Lots of times it's easier to see straight down. Okay, so here's the original diene, and here's the dienophile. Now, substitution effects, what you want is you want electron donating groups on your diene and electron withdrawing groups on your dienophile. We'll talk about that more in chapter 15. So now the stereochemistry. Now this is the really important part. Because the reaction is concerted, everything happens in one step. Bang, it goes. It doesn't have time to freely rotate around this, and so what ends up happening is, if on the dienophile, the groups on this side are going to go one way, and then the groups on this side are going to go the other way, right? So there's two hydrogens here. So if we say, okay, these are going to be on wedges, that means these are going to be on dashes, okay, or vice versa. It really doesn't matter, okay? But in this one here, right, this side again, we're going to say, oh, hey, these are going to be on wedges, right? So there's a wedge hydrogen here. That means this side is going to be a dash, or vice versa. Okay? So if you draw it like this side has to go in one way, this side has, one of these is going to be on wedges, one of these is going to be on dashes. Doesn't necessarily matter. In this case, it doesn't necessarily matter which one you pick, as long as you're consistent. Okay? And so if we're looking at this, so if we want to see, how these things come together, right? What are we going to need? Notice how both of the, so I should say, start off, here is your diene, okay? So we know we're going to need this. There's nothing else hanging on it, so it's just like this. And notice here, we have to double bond because there's a single bond here. These are both on wedges, so that means that they're both on the same side here. So for this one, again, here's going to be our diene. But notice how these are on, one's on a wedge, one's on a dash. That means that the diene, one of them is going to be on this side, the other's going to be on the opposite side. So it's more of a trans configuration. This is because they're both on wedges. Okay. Now we do have to be careful with this one here. If they're both pointing out, this is pretty subtle. If they're both pointing out, they'll both be pointing the same way here. If one's out and one's in, you're going to get this mixture of wedge and dash. So for that for the diene. Now for here, okay, again, we just need to we need to push this out of the way. Okay, here's your diene here. You're going to bond, shift the bond up here. So here's your 6-membered ring, and again, you have the your bridge that goes between here. So this CH2 here is that CH2 there. And again, because it's all happening simultaneously, it's a concerted reaction. You don't have time to come in and rotate around the bond of the diene to move those things around. Now, this endo versus exo thing. So I said it didn't matter, wedges versus dashes. Okay, that's with when you have an open diene like this. When you have one like this where you have a bridge, then it actually makes a big difference. Okay, what you get is what's called the endo product. Okay, stuff like that. And so what ends up happening is you get, as these things come in, let's see if I can take a better picture. Okay, so as these things come in, right? So you have the, right? So I wish they would have drawn these out. What ends up happening is you actually get interactions between these pi bonds here. So you get pi-pi stacking, okay? And so these actually, like that. And so what's going to happen is they're going to be kind of coming underneath, okay? And so what ends up happening is, if this is coming from underneath, right, that's going to push the CH2 away, okay? And so what ends up happening is, you look on your diene, and you say, do I have something with an additional pi bond? If I do, so like lots of times it's going to be a C double bond O, okay? If I have the bridging carbon, or carbons, if they are going up, that means that that thing with the extra pi bond is going to be going down, that group, okay? And so with that, and so if you look at this, okay, so we'll go ahead and draw these out. Okay, so again, we're going to have, oh, so it's like this, right? So we're going to have that, that, that. And this is just a regular open diene, so no problem. It's just going to be the regular, right? This side is, let's say this side is wedges. So, see, yeah. That means that these guys are dashes. These sides are going to go together. Okay? Now, if instead, okay, I'll put it up here so you can still see it. If instead you had this, where you have these bridging carbons, right, like this, now it becomes an issue of endo versus exo. Okay? And so here, so the ethyl, methyl, ketone, hydrogen. Now again, you're going to have these 4 carbons coming in, bond, 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 okay? And so you're going to end up making, right, your normal cyclohexene. Okay. Now, again, we're going to have the CH2, oh, because to say the CH2, let's say, I usually say it goes up, okay? It's going to go between here, right? So we're going to have CH2, right? Now, because these bridging carbons were going up, that means a group with an extra pi bond on the diene is going to want to go down. So that group is this. So that's going to want to go down. Okay? That means this whole side is down. That means this side is up. Okay, so this means this. If this is a wedge, that means this is a dash. Okay, because if this was saying this is going to be up, that means this is going to be down. It's just going to be a dash, which means this is a wedge. Okay, and so we know dash, so CH3. So it means this is a dash. Wedge. Or wedge. Okay, so you can draw it either way. Okay, this is usually easier to see. Right? So because the bridging carbons are wedges, that means that this thing with the extra pi bond is going to be a dash. Since this is a dash, that means this has to be a dash, right? Because these follow have to follow the same way. That means this side is going to be the dashes. So there's your product. There you go. Good luck.